So this is a classic circuit. It's got a clock here. This is not a voltage source in the true sense, it's a clock. And then he's got a resistor here, R, and then he's got a capacitor here, and he's got another resistor here, R, C, and he's taking his output right here, V out, right?
Yes.
Is that right? This is the problem. All right. Now for the values, R and C, it doesn't matter. We can put them in if you want. What's the value for these R's?
1K.
They're both 1K?
Yeah.
Okay, perfect. They're 1K ohm. And what is the capacitor?
400 picofarads.
400 picofarads? All right. Now at that point, we start looking at what actually is the input here, the VS. And that's a clock. So first thing you look for at the clock is the amplitude. Is it 5 volts? The signal. Oh,
It's 100 dB. And
I'm sorry. This has got the, they give the input. Is that the input right here?
Yes.
All right, sorry about that. I was hoping I just wrote it up. So for the input, and that is input, right? He has this kind of a deal, an envelope like this. What's the frequency, the low frequency he's got there?
100 dB.
No, right here.
Oh,
Is that 10 to the 5th?
yes.
And that's at one, so at 10 to the 5th, right
That's
here, it's, what's the signal level?
100 dB.
100?
100 dB.
100 dB microvolts, right?
Correct.
All right, dB microvolts, important. So you divide by 10 to the minus 6 if you actually had the 8, yeah.
Just rising at plus 20.
Yeah, all right, so we got a rate of increase of plus 20.
Minus.
Right here, is that 10 to the 6th?
Yes. Yes.
I think I remember this one, 10 to the 6 hertz, and this is omega, by the way. And here, you can figure that with that out. That's one order of magnitude, right? Going up by 20 dB, that means this is going to be 100 plus 20 or 120 dB microvolts, right? You should have that on the
Yes.
caption. Then it starts going down to 20, or is it 40?
40 minus 40.
All right, so now this one's going down at 40 dB. Did we do this one?
We did, but I was questioning like.
That's fine. We'll just do the whole thing and get your calculators out. Make sure you can calculate this thing right. Because there's a quiz coming up, and I'm going to tell you one of the problems is you don't do the calculations enough times, and you'll make a stupid mistake. I'm going to tell you that. All right, now that's the input. Where does he want it at? The output voltage, right? At what frequency?
50th harmonic.
All right, you're way out here. This is omega naught, is it not? Isn't that right?
Yes.
If that's omega naught, it's 50 times that, or it's 5 times 10 to the 6, correct, class?
Yeah.
So out here is 5 times 10 to the 6, and he wants to know what the output voltage will be, right? So first of all, what's that signal level right there that would be going in? Well, the way we get it is we know at this point right here we're at 120 dB microvolts. Everybody got that? I'm not going to fly through this. I want to make sure you can see how to reason through it. Everybody clear? Now, we're not going 1 decade. Follow me? It's not 10 to the 7th. If it was, we'd just take minus 20 from that. Follow me? Or minus 40 in that case, right? So what we have to do to get the level of the signal strength right here, we start here, we have 120, it's dB microvolts, right?
Mm-hmm.
And then it's going to be minus 40 times the log of the difference in this to this, which is going to be the log of 5 times 10 to the 6th over 10 to the 6th. Now that means it's a ratio of the frequency you end up at divided by the frequency you start. I put the minus 40 out there because it's going down. Does everybody understand that? Now that's the signal level right here at the source. We haven't taken into account the filter. I want to make sure you see every part of this. Got it, guys? So for whatever harmonic that is, the 50th, this is going to be the level. Just give me this value right here.
92.04.
All right, 92.04 dB microvolts is what's coming at the 50th harmonic right here. That's the signal level, right? Now you have to account for what the filter does. Does everybody follow me? I'm going to make sure, I did this before, I want to make absolutely certain you see this. The way I recommend you do it, look at this as a single unit of impedance. And what I usually do is just call this something like ZRC. And then off to the side, just put, does everybody follow me what I'm doing here? Just put ZRC is equal to, well, it's equal to 1 over R, whatever R is, plus j omega c, whatever that is, right? But omega is going to be 50 omega naught. Follow me? It's the frequency that you end up at. All right? Make sure you understand. That omega is going to be the frequency you end up at. Everybody follow me in this class? I tried to make myself clear last time. I don't want to fly through this one, but I got to make sure you all see it. In the back there, can you guys see this stuff? All right. So now I have that as the input. Now what I'm going to do, I'm going to get the filter characteristics right here. I'm going to say h of omega for any value of omega, the general one, is actually going to be, it's the ratio of output to input, correct class? Output to input, which is V out of omega over V in of omega. And that's really going to be simply, in this case, just ZRC over ZRC plus R. Now I put it this way for a reason. I didn't put down the complicated form of ZRC that I have over here. I just abbreviated it. Got me, everyone? Now the reason I did that is because I'm going to divide top and bottom by ZRC. It's important you see this. Follow me? So when I do that, this becomes simply 1 over 1 plus R over ZRC. Everybody follow me. This is not hard. It's, as a matter of fact, it's trivial in terms of engineering. Now I put in what this is, but what is ZRC over there? It's this, right? Mm-hmm. Take 1 over that. Now you get 1 over R. Let me write it down. Now I have 1 over 1 plus R times the quantity, 1 over R plus J omega times C. Agreed? You know, no matter how many times I go over this, I still know that people mess this up. They do it, I mean, it's routine. All right, now, can everybody see R times 1 over R is 1, right? And R times this just renders this whole thing to be, and I'll put it up higher, my H here is going to be 1 over 2 plus J omega R times C. Does everybody agree? There's a 2, not a 1. Agree? Now, if that is H of omega, really, because my output technically is going to be H of omega times V in, right? Now I'm going to just put it here. I wish I had more board to work with, but V out is equal to H of omega times V in. Now, if we put this in terms of dB microvolts, right, because that's what our signal was given as, then you can see I would take 20 times the log of the magnitude of V out over 10 to the minus 6. Then this is going to be in output V out in dB microvolts, correct everyone? Then when I do this, that's going to be equal to 20 log here of the magnitude, I'll put V in first, V in over 10 to the minus 6, right? And it's going to be that plus 20 times the log, actually in this case, 20 times the log of what will be H of omega. Now, do y'all agree with that? I'm just sorry if it's a little messy, but y'all see what I'm up to? Now, what is this? That's this, what we just calculated. Follow me? Everybody see that? That is the signal, the 11th or the 50th harmonic. If you look at the input clock, that's what the value of that 50th harmonic is, right? So the only thing we need to do, we put that value in here, we have to evaluate that at omega's 50 or 5 times 10 to the 6th, really, right? Correct, class? Now you got to put the right frequency in. So when we do that, let me go ahead and just do this right here. So that means our V out in dB microvolts would be equal to the value that you got was 92.04 dB microvolts. Then it's going to be minus, well actually you can do it plus if you want, but it would be plus 20 times the log of the magnitude of 1 over this, which would be the square root of 4 plus, and then you would have 5 times 10 to the 6 times RC squared, right? square root of that, and you would get it, right? Now the trick is this, when you break this up, the log of 1 is 0, so you just have minus the log of this bottom part. Y'all follow me? What do you get for this, by the way? I hope I'm answering your question. I'm trying to go through every facet of this problem, because it's a good one. What'd you get?
Yes. 80.72.
Is that what the answer is?
It was like 83.
80, you got 80.72, not 83? Yeah.
Why you have a square root?
Well, if the magnitude is this squared plus this squared, square root, so this is omega RC squared, square root of it.
I
I can't hear you. I can't hear you. One person.
I got 83.01.
What was the answer in the book?
83.01.
Okay, check your calculator. I'm going to tell you that book's pretty good about being accurate. Did you get, because if you do this right, you take that, the magnitude of that is going to be square root of 4 plus omega RC squared, and omega is 5 times 10 to the 6. Just check, it should hit it right in the head. Are you with me? You might have left it as a 1 there. I don't know. Okay, did that answer your question? Yeah, I can.
Why do you have the square root?
All right, what we have to do is take the magnitude of this, right? Well, the magnitude of a plus jb is the square root of a squared plus b squared, right? A in this case is 2. Square that, you get 4. Then I have plus omega RC squared, square root of it, because it's a magnitude of a real plus an imaginary. You have to remember magnitude, okay? Anything else about this one? I don't need to fly through it, but we did this one. I know we did. You good on that? What? You want me to write it real neat? How about I break this up and just show you what you're really calculating? This is going to be minus 20 times the log base 10, it's a base 10 log, of simply 4 plus, and then the quantity 5 times 10 to the 6 times whatever RC is squared, and you have to take the square root of that whole thing. Now if you want to take the operator square root out in front, it becomes minus 10 times the log of just 4 plus whatever that thing is squared. And R is 1K and C is what, 400 picofarad, right?
I think it's just 4 plus 4 in there.
Is it 4?
I think if I'm doing the math right.
It may come down to that too. Yeah, you're probably right. That's the kind of problems this guy creates. But that should be, do you all see what I've done? There's nothing tricky. If I wanted it for the third harmonic, what would change really? Well, now you gotta go back here, right? There's the first. The second would be 2 times 10 to the 5th. The third would be 3 times 10 to the 5th. Got it? Find the input right there, find the level, right? After you have that, now find the value of the transfer function at the third harmonic, right? And minus 20 times the log of that 2 plus, or really 4 plus, then it would be 3 omega naught times R times C quantity squared, square root of that. Agreed, class? Remember, if you're on this side of it, you're going up by 20 dB, this is down by 40 dB, you gotta make sure you know which side you're on. And that's about it. Yes? No, okay, good. Any other questions?
Okay.
Outstanding.
That's what I think.
The problems I gave you weren't hard, but you had to be attentive to what we're doing. And by the way, this is really EMC stuff. This will be really good because here's a little insight into something. With FCC, when you get this information, say this is they give you this about the input signal. You got a spectrum analyzer or a network analyzer, you're gonna see this, all right? You can take a look right there and you can move the cursor and figure out the value right here. Now, you have to see if after you do your filtering that the output is low enough so it meets FCC regs. There's certain levels of output that are allowable and you gotta be below them. If it's mil-spec, it's a lot harder to meet. Mil-spec is much harder than FCC. In Europe, it's CISPRI. But really, you're always dealing in the frequency domain, almost always in dB microvolts for outputs that are allowable. When you get something like a laptop or a tablet, there's things called conducted emissions. It means when that thing gets plugged into a charger plugged into the wall, anything that goes right through that direct connection to the wall is a conducted emission. Right? They have all sorts of very hard rules about that, and they're values of the spectral contents voltage at frequency. If you go above it, you're in trouble. but they also have radiated emissions. So that's stuff that leaves, that's coming off that laptop and it's radiating, and they have a different set of standards for those things. But they're big, they're highly dependent on frequency, and usually we deal with electric fields. Our electric field is volts per meter almost all the time, right? The real world stuff, they take dB, microvolts, volts per meter. So if you had an E field of 10 volts per meter, it would be 20 times the log of that E field divided by 10 to the minus 6. That's the way they usually talk about electric field values in the real world when they're talking about any type of radiated emissions, conducted emissions, and for that matter, when you're doing sensor work and a lot of antenna work, you're in that. So it's dB, microvolts per meter. Follow me, class? Make sure you remember that. Because you'll see that when you go out to your first job interview. If you're doing anything with Wi-Fi stuff, you'll be getting that all the time. Any other questions? Okay. Next, I want to do one thing that deals specifically with a notorious problem that can be caused by lightning, unfortunately. It's a real problem. It's called common mode currents, and how to deal with them. We use something called, it's really a common mode choke. Now, let me give you a little background. And I try not to make this too hard. It's actually quite interesting. Here's the problem in a nutshell. If you have a device over here and you got a power supply, right? You got a power supply with a power cord. I'm not going to draw the ground connection, and I'm not going to talk about when you got plus or minus 120. This is the simplest possible thing, like the power supply that you stick into the wall that drives your laptops and tablets. The current's here in the differential mode. There'll be a current here. The exact same magnitude, opposite directional current will be in the other thing, right? That's called a differential mode of signal. It means what you're basically doing is sending current down one through the positive lead, it's returning in the negative, right? The net sum of the current crossing any straight line path is 0. Do you follow me? So if I look at the net current flowing that way, it is 0, because the same amount going one way is coming the other. Got it? And that's what you want. That's what you want. But here's the problem. And this happens. As a matter of fact, the first time I saw real EMC / lightning problems in the real world on a cell phone tower, it was related to this common mode problem, and it was with Adtran. Adtran's a pretty big company. But here's the problem that happens. All right, this is just my device under test. It could be your laptop, could be anything. And you have basically, this thing's something that goes to a wall jack like that, and that's going to be plus to minus 120 volts AC at a something. Now, if this thing's plugged in there, but somehow out of the blue, lightning hits here, right? Lightning is a single polarity. I mean, it's basically all either positive or all either negative current that comes down and hits. And it wants to go in every direction it can to get back to what's called a parent charge. And the way it gets there, usually, when lightning hits, it flows down the path of least resistance, which in this case would be your line right there. Now, it's going to flow down that line. You have a thing called a ground over here, right? You usually have that ground isolated. There's a lot of things. You'll have transformers here, but I want to make this problem real simple. You usually have transformers that'll come off, make it DC and stuff. You all follow me? But with lightning, because the actual signal has such an immense amount of voltage on it, it will jump right over this, arc right over. It'll arc onto the chassis and then go through the ground connection and out. So it'll fry your laptop. Has anybody ever had anything electronic fried by lightning? Anybody? I've seen TVs. I've seen, I think, some stereo equipment. If any time you don't have good lightning protection in a house or anything like that, when lightning hits, it takes out a lot of things. And the bad thing about TV is you got something called a cable. You have your coax cable out there that goes right into the back of your TV. Well, actually, nowadays it goes into what? It doesn't go into the TV anymore. It goes into a modem, doesn't it usually? Or a router? And then you have, from there you have it. Well, in the old days, it used to go right to the back of the TV. And in the old days, when I was a kid, they used to actually put wire antennas up there in the attic and hang them out the roof, and they would come down right to the back of the TV. I remember as a piano teacher I had, her name was Mrs. Flack, sweetest woman you'd ever meet in your life. She was in her living room and lightning hit. And it not only destroyed the TV, but she told me this, at first I thought she was nuts, but this is a real thing. You know what ball lightning is? Has anybody heard of ball lightning? Look it up. She had that happen. She said this visible ball that was hissing came out of that TV. It's a positive, it's an anomaly, a plasma anomaly. It's called, I think, the Bennett pinch. And it was floating in there in a room, and it got somewhere down the other side of the house and blew up something. And she was devastated by this. I was young, it didn't happen that way, no way. Then I read about it. And you know where they have this, just to finish the story? I ran into a guy at Dogden at the Naval Surface Warfare Center in Virginia who had dealings with submariners from World War II. And in World War II, they didn't have a nuclear navy. They used to have all these batteries, tons of batteries that ran the actual motor. It's a motor driven by batteries. When the subs were underwater, you couldn't burn gas because you didn't have enough oxygen. So when they take those offline, they have an immense amount of current, and the inductance in that system is immense. So they get these huge arcovers, and every once in a while they get balls of light. They called it ball lightning and stuff like this back in those days. Little balls, and they would float around. Sometimes they damage things, sometimes they wouldn't. And you can read about this if you look up ball lightning. Nobody really could give a good explanation of this until the advent of supercomputers. And then it's called a Bennett, I hope I'm saying this right, a Bennett pinch, it's Bennett, I think, pinch. And it has to do with the actual, you know how when currents in the same direction pull together? Y'all know that, class? Are you familiar with this? Currents in the same direction pull together. That it's actually the currents on the outside of that thing are in a mode where you're basically getting figure eight, and they're pulling together on the shell of that and holding all this really, I'd call it very hot air in there. It's thermally ionized in that thing. But it's an amazing thing. If you were, anybody looking that up right now? Ball lightning, do you see it? Is it, who's the author of the page?
I'm on the Bennett pinch.
Well, look up ball lightning, and then you'll see the discussion of it. It's amazing. Another thing I want to tell you about, just real quick, before we get into this, because this is really bad. The object here is to say that common mode currents, very bad. Anything you can do to stop those, very good. Problem is, if it's lightning, you need something that can withstand a huge amount of overvoltage, megavolts sometimes. All right? Just remember that. Lightning is really nasty to stop. When it hits, it's just duck. That's the only thing I can say. You don't want to be there. So I told you about ball lightning just because I thought it was an interesting thought. But the real problem is just a strike right there. It's called a cloud to ground strike that hits around. So how do you stop it? One of the easiest methods you can do, if the common mode current isn't too high, is this. It's called a choke coil. It's a common mode choke. If I had more time, I'd tell you a story about some guy that actually created a Bennett pinch. He chopped up a giant long steel rod to something exactly the same length. Unintentionally, by the way. Scared him. So this is a common mode choke. It looks like this. And we build these things all the time. You take a piece of ferrite, it's really a ferrite donut. That's all it is. And we have them upstairs. They're about this big. You can get them any size. You take the wires for your input voltage or current, and you're going to take it and just take them through like this. And this one, like so. And what you're doing is making a transformer. All right. Now, I won't get into all this, but you know by the windings, how many have had gross for power? If you had gross, you learned this. But the way you figure out where to put the dot on a transformer, everybody's had transformers, correct, class? How many have had transformers? You never had transformer? Did you take circuits? You didn't have any circuits?
No, we talked about it power class that covers it.
Oh, power, sure. Did you have power?
No.
Are you going to take power?
Probably not.
All right. Then I'll spend a little more time on this. Anyway, the dot convention has to do with the way you define voltage-current relationships. Just listen to me. if this is I1 here and this is I2, right? The dot convention says that the fluxes, if you put the dots on the same terminal, that means current going in that way will cause a flux to flow in a direction that will be the same as current on this one flowing into that one. The flux will be in the same direction. What it really means is this. With transformers, what you have is this. And I'm going to break it out in standard model. When you have a transformer, you're going to have a dot here. If you haven't had this, just write this down. I'm going to make it very simple. You have two windings. There's a primary and a secondary. Doesn't matter what you want to call it beyond that. Primary and secondary. You're going to have a voltage here. Actually, let's do this with a coupled. We'll do this with a coupled circuit, not with a pure and ideal transformer, because this will be better. This is not an ideal transformer. So this is going to have a mutual inductance there called M. There's going to be a self-inductance on this coil, L1, and a self-inductance on this coil, L2. There'll be a voltage on the primary side called V1, and a voltage on the secondary side called V2. All right. Now, the relationship, and there's going to be a current, always direct the current into the dotted terminal, I1, here, and a current into the dotted terminal here called I2. The relationship between the voltage on the primary and voltage on the secondary with respect to the currents is given by the standard coupled circuit and mutually coupled circuit equations. It means that V1 is equal to J omega times L1. That's the self-inductance, so this is like the impedance to the coil, all right, the primary coil, times I1. That's all it is. And then there's a mutual inductance, J omega M. M is mutual, that's the symbol there that I use. You may have seen L sub M, it doesn't matter what symbols you use. M means mutual, it's between the coils. It's not a self-inductance. And then it's times I2. Then V2 here is equal to J omega times M I1 plus J omega L2 I2. Now that's the relationship between the voltage and currents in the primary and secondary for a mutually, or really for a magnetically coupled circuit. I could make that into a transformer if I took L1 and L2, multiplied it by themselves, and then said that was equal to M squared. That would be a transformer where the coupling was good, and then these would break down to simple transformer equations. But because this isn't a highly coupled, this isn't something, if you do this, it's not going to be super highly coupled. But one thing you can say with this, usually the turns on the primary, or the turns on one side or the turns on the other side. So L1 is about equal to L2. And that's about equal to M also. About equal to M. About. Not quite. Now I'm going to show you how these equations work, and I'm going to slow down here. Y'all remember that? How many remember that right there? Some variant of it. All right. How many have not had transformers again? You have not had transformers at all?
Correct.
Do y'all know what I'm doing here then? As far as that winding? You know what an inductor is usually just a coil. The dot just indicates the sign convention where you assume current into that will cause a plus to minus voltage as shown it. V1. On the secondary, current into that dot causes a voltage plus to minus as shown. I'm surprised you didn't get transformers in circuits. Really? Things have changed. All right. It's very important, but this is mutual. This is really a coupled magnetic circuit. So those are the equations. Now, this is how you make it. How you make the thing, just like this. Just wind wires and you'll do it. Now, getting back to how to stop these common mode currents using that. Here I'm going to take it over here, and I'm going to say this is really that, only I've got it. Instead of laying it on its side, I put it vertical so you could see it better. Now I'm going to lay it on its side. I'm going to show you what you have. This itself looks like this. Here's L1, L2, and then the coupling, M, between them. Now, here, you can say that that goes to a device, and we're going to have a current I1 here, and we're going to have a current I2 here. Keep an eye on this. Now, I1, I'm going to say, is defined as something called a common mode current. That's I common. Common mode means the current's the same direction, same magnitude in both. Do y'all follow me in this class? Common mode means it's just the same, it's common. The same exact current flows in the same exact direction. But it also has a differential current. Now the differential current is the one you want. That's the one that goes down and comes back. Same magnitude, opposite direction. Do you follow me? You don't know what the values of these are yet. Here in I2 you have I common, but it's minus I differential. All right? And again, you don't know what common is, you don't know what differential is. But now what you can do is take a look at what happens as far as the impedance of this thing to a common mode current versus the impedance, and I'm looking right from here to here, right here, the impedance for common mode versus differential mode. Can you all see why I'm doing it? I'm not even going to put a load out there, I'm just going to put a short for now, all right? I want to show you the difference. So when I do that, I'm going to use this board. Here's what happens. When I come here, remember I have V1 here, right? And I have V2 here. Are you with me? Now, what I'm going to do is do it for just the common mode first. So for the common mode, I have something where I have something here and I have L1. I have a current, I'm going to just call it I flowing there. And I have a voltage V1. Then I have a current here, right? And I'm going to have a voltage I2, or a current I1. It's going to be the same. I can just label it I common, flowing in there. And I'm going to have a voltage plus or minus V2 here. Now V1, and by the way I'm going to connect these things is this. I'm just going to connect them together like that. I'm going to ground that. But what I want is the impedance looking that way. As a matter of fact, let me do it this way, because this is the way it's usually done. We're going to get the net impedance in this little loop. All right? Just watch. I'm going to get the impedance of this plus the impedance of this. Now when I look at this, when I look at V1, I know it's equal to J omega L1 times IC, right? Plus J omega, and now it's going to be the mutual. Should put the mutual here. This is L2, and this would be the mutual M. J omega times the mutual, but you'll notice the current's flowing in there, so it's going to be a positive I common here. That's V1. Now watch. So what is the impedance of that coil where the voltage V1 is? If I look for V1 over I common, that would be the impedance of the coil in common mode. It's just one coil winding. Here, can you all see how it becomes just J omega, and then it's L1 plus M. You all see that? Now that's the impedance of that coil. So it's J omega L times M plus, or J omega times L1 plus M, and that's the impedance. So literally, that's the impedance of this. If you want to put an impedance, just an impedance to replace it by, that's what it would be for common mode. Y'all believe me when I say this will be the same, only it will have L2? Are you with me on that, class? Because it's the same exact effect. Current going this way, V2 would be J omega M IC plus J omega, and then it would be L2 IC, because IC is flowing into both dotted terminals. Agreed? Are you with me? So that means here, the net impedance right here, or the effect on the common mode current, Z common, and this is the total, would be equal to 2 times J omega times, really, in this case, it's going to be L right here. Actually, I'm just going to say if L1, I'm going to make L1 equal to L2 because that's the way it is in the real world all the time. So it's really going to be 2 times J omega L1 plus M. And what this amounts to is, it's twice the impedance on this coil or this coil in common mode. So that's Z common. Follow me? And that would be the impedance that would be against common mode current. When this is large, like 10 to the 8th, right, or so, then that's a large impedance that's going to stop any significant amount of current from getting through there. You're going to have to go with me on this one as I make it clear with the differential. Now with the differential mode, that's common. With differential mode, here's what happens. Now I have this, and I'll connect them like this, and if I want the impedance here, I know I have a current I differential here, but the same current I differential coming back that way. Are you with me? I didn't put a load on for, because I don't want to. Do y'all see this? And the only thing I want is the impedance across these terminals. Are you with me, class? So what would it be? Well, this is voltage V1, right? So V1 here would be equal to J omega L1 times I differential, right? Then it's plus J omega M times the current entering this one. Do you all see that that's minus IV now? It's negative, right? Because the current's not entering, it's leaving. The way you adjust for that is put a minus sign. So this is really minus J omega M I differential. Can you all see that? Are you with me? And this is the bottom line of this. So what is the impedance of this coil to differential currents, the currents that you want to get through? Well, if I take V1 over I differential, it would be the amount of impedance one of these coils is going to present to the differential current, right? And what's that going to be? It's going to be J omega, and then it's going to be L1 minus M, right? Now, if L1 and M are about the same, you see it's zero impedance for the differential current. Do you all see this, class? Can you see this? It means it doesn't affect differential. If M is about equal to L1, if they're within, say, 0.1%, 0.2%, then effectively what you've got there is a zero impedance to the differential current. And where is the impedance going to occur? It's when it's common mode currents. It's going to stop that. And that's the idea of this whole thing. When you do it this way, this little device right here is an amazing deterrent to common mode currents, and it's cheap to make. Now the problem with this in the real world is this. This wire here is insulated, usually with insulation that can take maybe 1,000 volts, right? It's, maybe there's 30 turns, so it's 30 times 1,000, 30,000 volts more. Anything more than that will go right over that coil, it'll break it down. So what you need to do when you do these things for lightning protection work, you have to have insulation on those wires that will really be something where, if you wanted something against, say, 1,000,000 volts, what you would do is say one wire's next to the other wire would have a voltage rating that would be equal to, what you do is take 1,000,000 volts divided by the number of turns, and that has to be the breakdown potential of two wires next to each other where the insulation's touching. Now actually you want to go way beyond that, to tell you the truth. You want maybe 10 times that because you don't want a chance of arc overs. But that's what you have to deal with in the real world if you're dealing with common mode currents caused by lightning. Remember that common mode currents can be caused by other things. They're called ground loops and stuff we'll get into. But lightning is the troubling one. And in the real world, you probably know that. And now, it's quiz time. Can you turn on the lights?